Hello everyone, my name is Mihaela Ștefan. I am a professional services engineer at Infinite Wireless. Thank you very much for taking the time to join our webinar. Today we are going to discuss about the routing capabilities of our Infinite Wireless devices. This is the first part where we concentrate on static routing and ODR, while the second part details the dynamic routing protocols. Let's begin by explaining the concept of routing, which refers to the process of determining the best path for packet delivery to the intended recipient. The routing process is connected with the analysis of the network layer headers for each packet. Often the IP protocol is used as the network layer protocol, and the router operates based on the following principles. It provides connectivity between different networks. It processes network addresses, not host addresses. The destination address is used for routing the packet. And the routing table is checked to determine the path towards the destination network, determined from the destination IP address. Let's look at a network scheme. We can see two local area networks, LAN 1 and LAN 2, that are connected using routers R1 and R2. In order to transmit data between PC1 and PC2, which are in the same subnet, the local switch will be enough. However, in order to transmit data between PC1 and PC3, which are in different subnets, the routers need to perform the task of choosing the best path to reach the destination hop by hop. Each router along the wide area network path will take its own routing decision based on the destination IP address. The following sources are used for filling the routing table. Kernel routes, represented by the service networks used by the device's operating system. For example, 127.0.0.0/8, which is the local network, as you know. Next, we have the directly connected networks, or the networks to which the device is directly connected. The interfaces of the devices will use IP addresses from these connected networks. Another source are the static routes, which are routes that are manually added by the network administrator. And last, we have the dynamic routing protocols, like, for example, RIP, OSPF, BGP, that we will detail in our next webinar. The routing table stores the information about each known network using the following format. Network address, which is the destination IP network address with its corresponding network mask. The gateway address, representing the IP address of the remote directly connected device to which the processed packet will be transmitted. Output interface, the interface of the local device through which the processed packet will be sent. Distance, which shows the trust level with respect to the routing source. And metric, which is a numeric parameter that determines the route selection in case of having the same distance value. As a note, it is best to have a lower value for distance and metric when selecting the best route. So the best route will always have the lowest distance or metric value. The routing table analysis is performed in the following order. First, the destination IP address is checked if it belongs to any of the networks in the routing table. Among the found entries, the most specific route is used, meaning the network address that best matches with the destination IP address. If the subnet masks are equal for the selected entries, the device parameter is, the distance parameter is analyzed. The smaller the distance value, the most trustful is the routing source. For example, for directly connected subnets, the distance is 0, the lowest available value. And for static entries, the distance is 1. If the distance is equal for the selected routes, an entry with a lower metric value is used. If none of the entries in the routing table matches with the destination IP address, the default route will be used, 0.0.0/0, which matches every packet, every IP address. If there is no default route, the packet will be discarded. Coming back to the routing table that we checked in a previous slide, let's see how will the different packets be analyzed by the router. Let's say our first packet has the source IP address 10.10.10.101 and the destination IP address 192.168.0.3. As we discussed when routing the packet, we are only interested in the destination IP address. In our case, 192.168.0.3 seems to match with both the second and the third entries in the routing table. However, the routing module will use the most specific match as we discussed. In our case, the most specific match is the second network in the routing table, as it has 28 bits matching with the destination IP address, while the third route has only 24 bits in common. So our packet will be sent through the RF 5.0 interface. In the next example, the destination IP address 192.168.0.53 doesn't match with the second entry, it only matches with the third entry in the routing table, so the packet will be sent through the Ethernet 1 interface. Last, we have an example with the destination IP address 192.168.1.53, which doesn't match with any of the specific networks in our routing table. So in this case, the unit will select the default route for routing the packet and send it through the RF 5.0 interface. Now let's review the routing capabilities of the Infinite Wireless units. The R5000 series offer full routing capabilities and are able to analyze layer 3 headers. You can configure IPs on all interfaces for both the management and the user traffic. You can configure static routing and dynamic protocols for the user traffic. Basically, the units can forward packets in routing mode like a typical router if appropriately configured. However, please keep in mind that Mint with the switching mode is especially designed for taking into account the quality of the wireless environment, unlike typical routing protocols that only consider the capacity of the link when computing the cost, and therefore might send the packets through a link that is temporarily affected by interference, for example. The other product lines, the Infinix XG Quanta 5 and Quanta 7T, are especially designed for backhauling and transmitted the packets at high speeds, so higher layer protocols like IP are not analyzed for the user traffic. They work only in switching mode for the user traffic, but you can assign IPs for management and configure static routing as well for ensuring a proper remote management of the units. Let's now see how can we practically establish layer 3 connectivity between two different subnets using the R5000 units in routing mode. As you can see, PC1 and PC2 are in different subnets, so in order to send data between the two PCs, we need to configure static routes on the R5000 units. We'll first assign IP addresses on the interfaces of the units. For the RF interfaces, a common subnet is used, while the wired interfaces of the units belong to different subnets, the corresponding subnets connected to each PC. We'll assume that the PCs are configured with IP addresses and static routes, the wireless link is established between the units, and the switching module is disabled on both units. Let's see how this is practically done. Okay, I have connected to the slave unit according to our scheme. Let's check the configuration. Okay. I am directly connected to the unit using the default IP address of the Ethernet interface. As you can see, we have no IP address for the RF interface and no SVI. Also, the switching is disabled as we discussed because we are going to use the units in routing mode. Since the most configuration for routing is performed from CLI, it is best that we assign IP addresses also from the CLI, because if we might assign, let's say, IP addresses here and add static routes in the command line, we might have inconsistencies in saving the configuration of the unit. So let's proceed with the configuration from the command line. I will not change, in this case, the IP address of the Ethernet interface, because it's exactly the one that we are using in our setup. So I will just configure the IP address of the RF interface. Okay, this should be it. Now let's check briefly the routing table. As you can see, we have here the directly connected networks. This is the local area network, okay, and this is the network on with the link towards the master unit. We do not have any information in the routing table about the network that is directly connected to the master unit. So in order to communicate with the local area network behind the master unit, we have to add a static route, and I will just show you how this is done. Okay, so in this configuration that I entered here, I am adding the network that is directly connected to the master unit, which is 10.10.10.0, and I am specifying the gateway, which is the IP address on the wireless of the master unit. Okay, so this is the gateway IP. Next. Okay, as you can see, now we have information about this network that is directly connected to the master unit. And it tells us through which interface will be each packet exited, which is the RF interface. So this is all we have to do on the slave unit in order to configure static routing. We just have to add IP addresses and a default route towards the connected network on the other side. Okay, I will just save the configuration. Okay, now let's switch to the configuration of the master unit. Okay, I am as well connected directly to the unit using the default IP address of the Ethernet interface, and we have switching disabled. I will go directly to the command line and show you what we have to do. In this case, we have to add a different IP address to the Ethernet interface because it belongs to a different subnet. So we will say if config 10.1/24. Okay, this is the new IP address of the Ethernet interface. We need to delete the other IP address because if let me show you the configuration. If I show you the configuration, you will see that now the Ethernet interface has two IP addresses, and we have to delete the default IP address, and we will use this command if config Ethernet 0 delete. Okay, this deletes the first IP address that was added. If config Ethernet 0 delete deletes the IP addresses of the interface in the order in which they were added. Since I was directly connected to the unit using this IP address, I have now to change my IP address. Okay. We are back on the unit with the new IP address. Okay, and we will continue with our configuration. So the IP address of the Ethernet interface is correct. I will just add the IP address of the RF interface. Okay, let's check the routing table. As you can see now, we only have information about the directly connected networks. And again, we have to add the static route towards the local network that is connected to the slave unit. So I will say route add. Okay. Okay. Okay, so now we have full information on the master unit in order to route packets towards the local area connected to the slave unit, which is 10.10.10.0. Okay, so this is all you have to do in order to configure static routing for a point-to-point wireless link connecting two different subnets. I can save this first. Let's now briefly review the dynamic routing protocols. The dynamic routing protocols can automatically create entries in the routing table, maintain the routing table up to date, and imply an easier configuration compared to static routes. The dynamic routing protocols are categorized into distance vector protocols or link state protocols. Let's check the differences. The InfyLink 2x2 and InfyMan 2x2 family devices support RIP, OSPF, and ODR as dynamic routing protocols. RIP is a distance vector protocol, while OSPF is a link state protocol. These types of protocols have the following differences. The type of information exchanged between the routers. Distance vector protocols exchange full routing table updates, while link state protocols send information about directly connected links to all the routers in the network. Another difference is the amount of service information stored on the router. Distance vector protocols store information only about directly connected neighbors, and link state protocols help each router to build the full network topology, so all the devices have visibility in this case. Also, the algorithm used to select the best route is different. Let's now discuss on-demand routing. ODR is a protocol for distributing route information used in star-type network topologies. The point-to-multipoint topology that you can see in the picture is as well a star in its meaning, so ODR is widely used in wireless networks. The ODR algorithm compared to other dynamic routing protocols is very simple, as you will see. From the list of features of the ODR protocol compared to static routing, we mention that it is easy to configure. The basic ODR configuration involves only role allocation. Scalability, increasing the number of devices in the network, does not require additional work. It is enough to pre-configure the devices and define their role. Efficiency, the state of the devices and of the links is constantly monitored by the ODR protocol, so changes in the network topology will be instantly reflected in the routing table. Redundancy and load balancing, the setups for increasing reliability and for load balancing do not require additional configuration. Everything is performed automatically. Let's mention again the topology restriction. ODR cannot be applied in networks with an arbitrary topology, and it is intended for star-type networks only. Last, ODR implies a proprietary implementation, as the transport technology for ODR is not standardized. The Infinet devices use the Mint proprietary protocol for implementing ODR. Let's now review its functionality by using the example in this slide. The ODR protocol has two roles, hub or the central device and spoke or the dead-end devices. As a rule, the hub device is the base station, which has a connection to the backbone network. The dead-end devices are the subscriber terminals, which are directly connected to the end user's devices using different subnets, as we can see in the picture. The hub sends messages to all the other devices in order to communicate its role as hub. The Mint protocol service fields are used for encapsulating the ODR messages. When receiving the message, the devices defined as spoke form a list of hubs. Since the star topology assumes that the hub has a connection to the backbone network, the devices having the spoke role can add a default route to the routing table by specifying the hub's address as the gateway. A single mint area can have multiple devices with the hub role, so each of the spokes can have multiple default routes in their routing table. Additionally, each spoke sends messages containing information about its directly connected networks and the static routes located in the device's FIB. It is important to note that information about the networks shared with the hub is not included. Last, let's remember that Mint uses an internal metric that reflects the radio parameters of the communication channel in real time and their current load as well. So the criteria for selecting the default route is to use the lowest metric value. The metric analysis is for each of the devices having the hub role is performed permanently. So if the metric of the current default route increases, it can be replaced by another one having a lower metric. This is how the redundancy and load balancing functions are implemented automatically by Mint. I will connect to the base station now. In order to configure ODR, all you have to do is you have to go to link settings and at ODR specify hub or spoke. So normally ODR is disabled. Then you have to select hub or spoke. As we discussed, the base station should be hub. So I will configure it as hub, apply. I already configured the slave units as spoke because it is very simple. And I will just now show you in the command line the status of the ODR protocol. So if you issue this command, you will see that the current device is configured as hub, and it has a list of 2 active spokes, CP1 and CP3, as you can see here. So this is all you have to do. ODR is very simple to implement. It just implies configuring the role, and it is suited for star type network topologies where you do not need to configure static routing and anything else besides IP addresses on the interfaces. So keep in mind that you still have to assign IP addresses to the interfaces, but you do not have to add static routes. ODR will do everything automatically. Okay, this brings us to the end of today's webinar. Now, if you have any questions, please feel free to write them down in the chat section and I will answer them one by one. I will review the questions now. First, we are asked if any of the Infinet devices support radius authentication allocation of IP via PPP. Okay, so we use the Radius server only for authentication on our R5000 units, where you can configure the rejection of the subscriber terminals when connecting to a base station based on the IP address, but it's not for allocation. For dynamic allocation, you can use the DHCP. Okay, so dynamic allocation of IP addresses is done via DHCP. Next, we are asked if ODR can be applied to point-to-point link. Yes, you can apply it to the point-to-point link, but usually to point-to-point links, we configure static routings because it is also very simple. Next, we are asked if we should set IP addresses on the RF in order to create static routes. Yes, let me tell you again, when we are using the units, the R5000 units, I mentioned again that only the R5000 units can be used in routing mode for the user traffic. You have to add IP addresses on all interfaces and you have to use different subnets on each interface, okay? So for static routing, dynamic routing, ODR, you have to assign IP addresses on all interfaces, including RF, and they have to belong to different subnets. And after you assign the IP addresses to the interfaces, you go on with the configuration of the specific protocol like ODR. So the first step, as I showed you in the configuration, is to assign IP addresses on the interfaces. The next step is to configure the protocol that you require or static routing. I hope this is clear. For XG or Quanta 5, no, we do not plan to add routing capabilities for the user traffic because they are backhauling products. They need to transmit data at high speeds. They do not connect directly to the end user's network. Okay, so you do not connect an XG directly to the user's devices, and all the packet header analysis is done on the device that is directly connected to the customer's network, which in our case is R5000 or another device that can perform this analysis. So XG and Quanta 5 will not have routing capabilities for the user traffic, only for the management traffic. Okay, I think we can end this session. Thank you once again for your time, and I hope to see you again during our next webinar. Have a nice day, everybody. Bye-bye.